This video is about how to measure small variations in the noise floor by use of an rtlsdr. Here is the setup parameter for the hardware, and the sampling rate is 1 megahertz. Gain mode is typically 3, that means sensitivity. This function is intended for people using some VHF frequency as an intermediate frequency for microwave. It could be 144 and the signal frequency could be, let's say, 10 gigahertz. And the operator is interested in finding the optimum position of the antenna, which might point to the moon. And the moon is warm. It's maybe 200 degrees, while the sky behind is very cold. And there will be a small difference in the noise received. And by looking at that noise, the operator can optimize how the antenna is pointed. So you see here the settings for the RTL dongle. And very important, the output has to be disabled. And then I go to the SSB screen, that's D, and it doesn't matter which mode you select, but I'm now using SSB, and I click at the center where we have a spur. And you can see here we have a spur at 144.0. That's an internal spur of the dongle. There is also another spur at 144.050. That is something I intentionally have added to show the problem of spurs better. The parameters I'm using here, X and P, it's not critical what you set for the bandwidth, and also not critical what you set for the window. The fastest version of FFT is number 4, at least on this computer, and first FFT number of B threads, I make it 1. That distributes the workload over more cores. First FFT amplitude 20. The dongle is an 8-bit unit, so the signal is, like always, using the highest bit, but the noise floor is only 8 bits down in the high bandwidth of 1 megahertz. First mixer bandwidth reduction has to be 1, and more important, the output sampling speed, I have set that to 400 kilohertz. That's why the sound card has to be deselected, disabled, because the sound card cannot do 400 kilohertz. And this computer is not fast enough to do much more than 400 kilohertz, so that's why I've set this. The more bandwidth, the better, because you get your result faster. So here we are again, and I click on the signal, I mean at the middle of the spectrum. I can center it by clicking on the signal here. And we have the two spurs. I will switch off one of them while looking at the S-meter graph. That's here. And you can see, was it 4.5 dB for this signal that is 35 dB above the noise in the wide spectrum. This is not acceptable if you want to look for moon noise, particularly if the amplitude of the spur changes as you turn your antenna. So we have to apply a notch on this frequency here. That's done with this box here. It says 0. I click on it and put in now number 1. Means notch number 1, position 0, and I make the width, let's say 20 units. And here you see a nice notch surrounding the signal. It wouldn't have to be as wide as this, but I make it this wide because there could be some frequency drift or something. Well, maybe a little bit less. I change it from 20 to 10. It's a small fraction of the total bandwidth, so we don't lose much of the noise that we want to measure. Then this second spur, that will be the second notch, so I click here and feed in number 2. And I have to give the position, and I don't remember so well. Let's try minus 150. And it comes here. So minus 230 might be a better guess. Oops. Position minus 230. That's pretty close. Minus 250. This is very unpractical. It should of course be automated, but I haven't done that yet. Nobody asked for it, by the way. Width, let's make that one also 10. And you can see on the S meter, the notch killed the spur. And you can see the notch is on the spur here. Now we can look at the noise only. And you can see, you can very quickly see changes that are in the order of half a dB. I can expand the scale. And if you want to see 0.1 dB, run it slowlier. That's here. Now you can read a change of 0.05 dB within 5 seconds or something like that. This is probably suitable for people with microwave interests. It is possible to read the average of the noise. Place the mouse somewhere, press down the left key, move the mouse and release. And here we have the average over a range of 331 points. It's minus 49.76. The second RMS value, that is the RMS deviation. It means the deviation of the individual points from the average, that is 49.768. In later versions of LINRA, this will be called DEV, D-E-V. So the error in the upper value here, 49.768, should be 0.019 divided by the square root of 331. That's a very small error. The stability of the dongle is not compatible with that, I think. I will check that. It's obvious there is a stability problem in this dongle. I'm now running with 1 point every 4 seconds or something like that. So, but the resolution is high. The drift from here to here is 0.02 dB. So with stable hardware, and if you are willing to wait half a minute, you can get very high precision on noise floor measurements. I press T to get timing information. The critical timing is here, narrow band signal processing. It's 85%. I can make X and P for parameters, and then enter, and I select third FFT window, power of sine, now instead 4. That is a better window, but it will have a cost. And click on the signal and press T. T. Not very significant. And I apply the notch again at 0. That's 1 here. And then the width again 10. And now you can see the notch is deeper. And you can see also that the sides here are sharper. So a better window gives steeper curves on the baseband, but cost a little bit more in CPU. Should cost more in CPU, but now it's only 67. I don't really know what's behind that. Maybe it's simply that the sine squared is a special case that isn't so efficient in this case. Probably because of how the cache memory is used. Anyway, having only 69% usage, I can go X, P, enter, and ask for a little more bandwidth, let's say 500 kilohertz. And then again I press T, and now we are at 80%, and going above that is probably not a good idea. But there is a little more bandwidth now. I can move this out, and you can see we have more noise. Significantly more noise. And of course, well, I have to with more noise comes better statistics. Means results come a little faster. And of course this depends on your computer. And I'm running very slowly, so you can see that the main effect now is not the random noise, it's the drift. Probably a temperature drift, but I don't know where. Now, a little later, you can see that the drift looks like an exponential, some temperature stabilizing. One thing is I forgot to add the second notch, so we have this spur contributing. So I remove that, and also the center spur, which I also forgot. 1 and width 10, and then the other one, number 2, and was it minus 250, I think. Well, we changed the speed, so now it's a different position. Minus 240. Minus 240. It's here. Minus 237. Minus 235. And width 10. And you can see it should be a little bit above. Minus 237. Now it is exactly at the center. So it's attenuated by, what is it? Something like 130 to 60. That's 70 decibels. So it's really not present anymore. And the two spurs, they made a contribution, which at this scale is rather significant. It's 8 decibels in total for the two spurs. And then I look at the noise only. It's here. And then wait for a while. Now, 15 minutes later, here is the noise floor in 500 kilohertz bandwidth. Could be compared to the noise floor a little bit earlier in this video, but I have forgotten what level it was. I opened the window for a couple of minutes and then closed it again. The outdoor temperature is about 10 degrees below the indoor temperature, and there is no wind. Today it's totally calm. So it's obvious I have a temperature problem in the gain stability of this system. If you want to use the RTL dongle for precision measurements of noise, a good suggestion is to bury the dongle in a big bucket of sand to give it a very long thermal time constant.